Okay, in a way, quiet. We're kind of bouncing back to chapter 7, but actually the homework is going to come from chapter 8. But this is where it combines the solving of systems in chapter 7 with the matrices in chapter 8. So, remember when back in chapter 7, we had already done, this is how you solve a substitution, this is how you solve for elimination, and then there's going to be a new one, which is using what's called back substitution for systems that are in what we call row echelon form, which you'll see in a minute what I mean by that. That's what we mean by row echelon form. The system is, right, it's got one of the equations only has one variable. So obviously you know that one already. The next equation only has two variables, including the one you already know, which means you can solve for it. And the last one, plug in the two variables you know and you find the third. This here is called row echelon form. And back substitution just means, again, z is 3, so we know that one. In order to find the y, we'll back substitute. Y equals 3 times 3. Oh, sorry. That was wrong. Y plus 3 times 3 equals 6. So y plus 9 equals 6. Y equals negative 3. And then now that we know the y and the z, we're going to back substitute into the first equation, 2x minus y plus 5 times 3 equals 22. Right. 2x plus 3 plus 15 equals 22. 2x plus 18 equals 22. 2x equals 4. X equals 2. So we have a solution. It involves 3 variables, right? And this is because a little bit, it's not really, because we get into 3, not just 2 dimensions with x and y, but 3 dimensions with x, y, and z in chapter 11. This is not just about the way that we're doing things a little bit out of order, because that would have followed anyways. But this is representing the intersection not of 3 lines, but of 3 flat surfaces, of 3 planes. If you remember from your geometry days, the intersection of 2 planes is a line. And then if you intersect that line with another plane, the intersection could be one unique point. And that point would have the coordinates in the 3-dimensional coordinate system of x, y, z. In this case, it would be 2, negative 3, 3. So it still has a graphical meaning to us, right? But does it have to? I mean, again, systems of equations wise, I can tell you that the system of equations, what we call the primitive equations in weather, are 7 equations and 7 variables. Okay, we're a little beyond I can represent this by space, right? That makes sense to us. I mean, maybe you can do 3D space and then add a 4th dimension of time as things are changing. But then what are you going to do for 5, 6, and 7, So they don't always have a physical representation, but these definitely can have a physical representation. Right. Now, when the system is not in this row echelon form, you can put it into the row echelon form doing what we did last time, the row operations. We did them with matrices, but you could do them with equations too. These are the same things, right? So by adding and subtracting, multiplying, here's our row operations. Interchange 2 equations, right? You could just switch their positions. Multiply one of the equations by a non-zero constant, right? Add a multiple of one line to another line and replace one of those, right? All those are things you're allowed to do, and you still have an equivalent system of equations. So this is not the row echelon form, right? Because if it was row echelon form, it would have zeros here. so that then it would be, you could solve the last one for z and then back substitute to solve. Then once you've got it in that form, then that's how you solve it. So do row operations to put it in row echelon form, and then solve it like we just did. Yeah.
So if it was negative z equals 2, that would still be a row echelon.
Sure. I mean, you might have to do a little bit of solving on the last one, but since there's only one variable, it would be a simple thing to solve, right? It didn't have, the last one, it was z equals 3. It doesn't have to be, 1 times z equals, and you've got your answer there. As long as it's only one variable, you can solve it pretty easily. Okay. Now, that method of doing row operations, so you put it in the row echelon form, that's what we mean by the Gaussian elimination, right? That's the Gaussian elimination. Now, in the last lesson, when we were doing with matrices and we were putting something in the form where it had the identity matrix all on the left, if you go that far, if you do a row operation so that you've got the identity matrix on the left, that means your answers are all on the right. That's it's called Gaussian Jordan elimination. Still Gauss. Gauss always gets credit because he's the big guy. Okay, so let's say we wanted to do the same thing with this right here. Right? Let's solve this system by turning it into a row echelon form, and then we'll solve by back substitution. Okay, so we need to create zeros here, here, and here. And I'm going to start with this one right there. Right? What combination of rows could I do? Multiplying and adding. Yeah, I mean, what if we multiplied this one by -2? Right? And then we add it to this one. Yes. Okay. So when we do that, we're going to get, right, the first line is unchanged. Right? We're not changing the first line. We're only changing the second line. So x plus y plus z equals 6. The next line now will be -2 times x plus 2x, 0, right? And we don't actually have to write the 0 because it's not a matrix. Then we have -2 times y plus -y, -3y, right? -2y minus y, -3y. -2 times z plus z, -z. And -2 times 6 plus 3, -9, right? Okay, and let's, okay, I'm going to just take it one step at a time. So then we have 3x plus y plus z minus z equals 2. Okay, now how can I make a 0 in this spot? Okay, so let's take this line right here and multiply it by -3, and we're going to add it to the bottom one right there. And we'll replace the last line with that. So the first two lines are the same. X plus y plus z equals 6. -3y minus z equals -9. And then the last one, when I do the -3 times this and add, I get the 0, so nothing. When I do -3 times y plus y, -2y, right? Then -3 times z minus z, -4z. And -3 times 6 is -18 plus 2, -16. Okay. So I need one more 0 to have this thing in row echelon form, right? I need this one right there. Incorrect. What's going to happen? What if I did, because that's your instinct probably is, let's multiply this first one by 2 and then add it to this one. I'm going to introduce x to that. I just got rid of the x, so don't do that, right? It's going to have to be a combination of these two rows. So what would I have to multiply? I mean, you have to do like -2 times this one times 3 times that one, something like that, right? I mean, some combination of 2 and 3 multiplying. I forget because the next slide relates to this, and I forget which one I did, but how about I'm going to go like this. I'm going to go this one times -2, and this one times 3, and I'll add those up. All right, so now I've got the x plus y plus 6 doesn't change. X plus y plus z equals 6. The second line doesn't change. -3y minus z equals -9. Okay. And now we've got our math going on, right? -2 times -3y is 6y plus -2y times 3. They cancel. That's why we did it. -2 times -z, 2z, plus 3 times -4z. So 2z minus 12z, yeah. What's that?
Did you have multiplied it by -4 and then 6 instead of -3?
Sure.
You could cancel out the -4.
Well, if you multiply this one by let's say this one by 4, right? And then you get what, 4z? And then you have to multiply this one by 6. That's still going to multiply that. It's not going to cancel out. So, okay, let's try again. Let's see. -2 times -z is positive 2z. 3 times -4z is negative 12z. You add it together, you get -10. Right? Negative 10z. And then the last, 18 minus 48. -30. Okay, so there's your row echelon form. And the last one, you could solve for z pretty easily, right? Z equals 3. And then you can plug into the next one, -3y minus, is that a minus? Yeah, minus 3 is -9. So -3y equals, add 3, -6. Y equals 2. And then one more back substitute into the top line, right? We've got x plus 2 plus 3 equals 6. X equals 1. Right? That is using the Gaussian elimination to solve one of these things. Good old Gauss. Now, we could have done the same thing with row operations just using matrices, right? I took this, remember how we learned last time how to make an augmented matrix, right? Okay, that's what I did. I took our original problem and I made this augmented matrix. And then I did row operations on that. That's also Gaussian elimination, right? And I did the same math that we just did. You can notice that these numbers are pretty much the same, right? Not pretty much, exactly the same numbers. -10, z equals -30, z equals 3. Okay, so it all would have worked out the same way. But now we're going to learn the real reason that we're doing this, that we learn matrices and systems of equations at the same time. Right? If you want to solve linear systems using matrices, then the first step is you've got to write your linear system as a matrix equation. We're not talking about the augmented matrix. I'm talking about a matrix equation where you take the coefficients of the 3 by 3 on the left side, and that becomes your A matrix. So notice the 1, 1, 1, 1, 1, 1, 2, -1, 1, 2, -1, and 1, 3, 1, -1, 3, 1, -1. the X matrix, which is multiplying, is the variable matrix, X, Y, Z. And then on the other side of the equal sign, you've got a B matrix, which is the right-hand side of these equations, right? 6, 3, 2. Now remember how matrix multiplication works. And we, always the question is, well, why would you define matrix multiplication to be like that? Because it allows us to do this kind of a thing, right? Notice if I was going to multiply these two, the A and the X together, right, then I would go across the row and down the column. I would have 1x plus 1y plus 1z equals 6, right? That's this line. The next row, for the second row, first column, 2x minus y plus z. That's this right here. Right? Because just the way matrix multiplication works, this is the same as this. 3x plus y minus z. 3x plus y minus z. So now we've changed this system of equations here into a matrix equation, where I'm calling this first 3 by 3 matrix is A. Right? This is the variable matrix X. The right-hand side makes up your B matrix. Now remember when we looked at this, right? We said the reason that we came up with inverse matrices is so we could solve something like this for X, right? You can't divide by A, but what you can do is multiply both sides by the A inverse. And when you do that, what do you get when you do A inverse times A? You get the identity matrix, and the identity matrix times X equals X. So that solves for X. On the right, you still got your A minus 1 times B. But that is all very easy to do in the calculator. Once you've already loaded the A and the B, doing A to the minus 1B is, seconds. And it solves it. And it would solve, a 2 by 2, a 3 by 3, a 4 by 4, a 10 by 10. I mean, it just loaded in there, A to the minus 1B, and you get it.
So when you do it, you don't even have to worry about X is gone.
Well, you'll see what you get when you do it in the calculator. I think I've got this one loaded. I think this was, let's see. I tried to preload some of this stuff. Load file. So this was example 3. I think I've already got it in there. So again, if I loaded these matrices in the calculator, I would go second, X to the minus 1 for matrix, edit, and pick 1. And I've already got all those in there, okay, just to save me the punching back and forth, right? And if I go to the second, X to the minus 1, edit, and look at the 2, right, it's a 3 by 1, 6, 3, 2, right? So once you've loaded your two matrices, then you go to the main screen, and again, pull up the A matrix, second, X to the minus 1, 1 for A. We want the inverse. How do I make the inverse? Hit the X to the minus 1, right? And now immediately do second, matrix 2. So A to the minus 1B. And you hit enter, X equals 1, B equals 2, C equals 3. Right? That's using matrices to solve systems. Again, we don't do much with a matrix above a 2 by 2 that we don't use the calculator anyways. So, I mean, this is not like me teaching you a trick to answer an Algebra 2 question on the SOL when you really have no idea what you're doing. This is actually using the technology the way it's supposed to be used, right, to enhance what we're doing. So let's try to do this next one. Try to do that one the same way, right? First, you're going to write your matrix equation, and then you're going to load the two matrices, and then you're going to do A to the minus 1B. See what you get. Did you get an answer? What'd you get, Pierce? I don't think so. 2, -1, -2 sounds right. If you didn't, I think I have that one loaded here too. File, load file. So let me make sure. Second, x to the -1, edit. So 231, 331, 241. I mean, the only place you're going to go wrong here is you enter the wrong numbers in the calculator, right? Because if everything's in there correct, you'll get the right answer. So let's see. Second, quit, clear. A to the -1b. So you should have got 2, -1, -2. Now there is one part of this. If you look at their definition, it says a system of equations with a unique solution, right? If A is an invertible matrix, meaning it has an inverse, meaning when you did the inverse, you didn't get an error saying singular matrix or something like that, then you can solve it by doing this. If there's no inverse matrix, you cannot solve. It means there is no solution, no unique solution. Right? So this is what it looks like when you have a unique solution. You'll get an answer like that. It'll pop up on the screen. Now, this is what it looks like when you don't. I think I got it loaded here. Yeah. This is what if you try to do this one and see what you get for an answer. Did you get something? So you should be getting an error message, right? Right? Singular matrix, which means, what it means is this matrix over here does not have an inverse. Okay. When I add these numbers in here, then it could be either that, again, if these represent planes, like flat surfaces that are intersecting, it could mean that there's no intersection point. Like 2 of these planes are parallel, so they never come together. Or you're never going to find one point that's on all 3 planes because 2 of them don't even touch, right? Or it could be that, let's say, if 2 planes intersect in a line, all 3 planes are intersecting in the same straight line, which means there's infinitely many solutions. You don't really know when you get this error message here. Is this one of those no solutions or infinitely many? The right way to say it is no unique solution, right? I mean, it's not going to be a unique solution. It could be that there's more than one, but in that case, it's not really interesting to us anyways. So that I would just say when I got that message, no unique solution. Done. So that is then our coverage of systems of equations. We did substitution, elimination, Gaussian elimination we saw today, and then the matrices. And there is one more lesson we're going to do next class, which will use some basic substitution elimination to do a thing that you will be asked to do in calculus. And they appreciate if we've at least talked about it here. So that's what we did. The homework is all coming from the section where you could just do this with your calculator, okay? So it shouldn't take you, what, 10 minutes to load these numbers and do them?